Hello, I'm Jeff Hunt, and today I'm going to take a look at the dangers of spray foams on roofs. So we're going to launch straight into some of the basic definitions so that we can all be clear on what we're talking about. So this is the traditional method of insulating pitched roofs by placing the insulation, normally fiberglass, on top of the ceiling line. So this has the effect of keeping the heat in the building by stopping it getting into the roof space, which makes the roof space cold. Hence the phrase we get when we do this, the cold roof principle. Let's go back to our original diagram. This is the pitched roof with no insulation. And now take a look at another way in which this is done. So this is the principle when spray foam is applied to the underside of the tiles or the underfelt between the rafters. And what happens here is that the warm roof rises above the ceiling line into the roof void and then is resisted by the foam on the underside of the tiles. And so this is often referred to as a warm-proof principle. Now these are the common definitions that are being used for systems applied to pitched roofs. However, there is a bit of a problem here, and that is because these definitions have really derived from a flat roof construction, and so there can be some misunderstandings. So let's take a look and see how this arises. On a flat roof, you can apply the insulation above the roof deck before the waterproof membrane is applied, and this in flat roof terminology is called a warm roof. The principal difference here is that the warm air from the room below heats the plasterboard, the rafters, the space between the rafters and the decking, which is not the same as the principle of applying the foam to an underside of tiles. So you can see that the warm roof principle for flat roofing is not the same as the warm roof definition that's being used in pitched roofs. If we go back to the way that foam spray is applied, what we have is technically often referred to as a hybrid roof, where insulation is placed at the same space, if you like, or layer as the structural rafters. And as I say, this is called a hybrid roof. So let's take a look and see what happens in practice when we apply spray foams to roofs. Well, generally what happens is that when we look at this example here, we've applied the spray foam into a roof that already has insulation on the ceiling line. So we get a joint effect of the warm roof and the cold roof principles. And this is where the anomalies start to arise. So here we have a diagram here of what happens as the warm air rises. So there's warm air in the house. It's sort of held back by the insulation on the ceiling line and then rises into the roof space, which we assume is still too cold. And then that energy gets trapped underneath the foam of the spray foam. But then we're assuming that that thickness is able to hold back that smaller amount of heat in order to reflect it back into the space which we were considering to be too cold. The net effect is that you can see that you've got two cycles of warm air now, with one set below the ceiling line insulation and another set underneath the foam. So you can see that when you actually try to add the two effects of the foams together, it doesn't quite work. And in fact, on quite a number of the BRE guidance, it says that you need to actually remove the insulation from the ceiling in order that the warm roof or hybrid roof principle can actually work as it was designed to do. So you can see there are many anomalies in these systems that, whilst they work in practice, in principle, in practice they can be very, very difficult to assess. So now let's take a look at what else happens in these types of roofs. And what I want to introduce now is the moisture that arrives in the roof and what happens to heat through this structure. So now let's assume that this style of installation means that there is no insulation on the ceiling line. And obviously if there is, then that would add additional complications, but let's take a look at the simplified form as it should probably be designed. And so we see moisture rising up from the house below into the roof space, along with the heat that now rises up into the roof space because there is now no insulation on the ceiling line. So you can see that what happens is that the moisture vapor is going to increase in the roof space, as is the temperature, and now they will both try to head out through the sides of the roof where the foam has now been sprayed. So we assume now that the foam has some form of vapor permeability to allow the moisture out of the roof. Now, when this happens, we need to think about the root of the moisture and the root of the temperature. So that's rather a strange concept, but as the energy moves through the insulation, the temperature gradient, as it's called, will drop. In other words, if you took the temperature on the inside of the roof, that should be higher than the temperature on the outside. So in all grades in between, the temperature must drop from one to the other, and that's called the temperature gradient. Now similarly, as the moisture vapor moves through the material, that will also carry with it the vapor pressure that has built up in the roof space as it tries to get outside. Now the problem comes when the water vapor meets the temperature drop, and if it meets the temperature drop at the dew point, then condensation will arise, and the most likely place that this will arise is on the outer edge of the insulation. And as you can imagine, all sorts of problems could arise at that point. So let's take a closer look at that particular layer. So here we have a little detail here of an expanded pitched roof. I've taken away the rafters and I've just thickened up the insulation just for a bit of clarity. So on the top there, that is the tiles, and we have two arrows, one representing the temperature gradient going through the foam, and also the journey of the water vapor as it moves from the higher pressure through to the lower, assuming that the felt is vapor permeable. And the new layer I put in is the underfelt, which can either be breathable or not, and we're going to take a look to see what happens at each of those junctions. Okay, so let's assume now that this is a non-vapor permeable underfelt, like a bitumen underfelt, and so that's represented by the sort of no entry symbol. And so what happens is obviously the temperature can go through, but the vapor cannot, and so it has to stop at this stage. And this is always a critical problem in any structure where we have vapor permeability, but then we suddenly get a layer that stops it all moving. And so what I want to demonstrate here is that when you consider the thickness of the foam, the largest temperature drop will happen across that foam, and the coldest temperature will be at the outer edge. Now that gives a great opportunity for the dew point to arise depending on the outside temperature, and there is every chance that rather than the vapor just moving around inside the foam, it will condensate on the layer that is non-vapor permeable. And this is a very great risk in these types of applications, so much so that it is not possible to apply insulation to the underside of a non-permeable layer. And this is a very common practice when we think about vapor check. The golden rule for vapor check is that you place it on the warm side of insulation, and the reason that this has been well known for many years is precisely because you don't want this type of situation to arise. So in any installation with spray foam roof, any application directly applied to a non-vapor permeable layer such as bitumen is absolutely not going to work. So let's take a look at this particular diagram, and this is showing that the underfelt layer is vapor permeable in some way, as is the foam in some way. And let's take a look at the overall principle of how this is to work. And essentially you can see the water vapor moving through the foam again. This time it reaches the underfelt, which is also vapor permeable and allows the vapor to pass through. You can also see the temperature gradient. Obviously that's going to be at its most highest differential between the inside and the outside of the foam, and so that is still the great danger point of where the dew point could actually occur. And this is in principle how these systems are supposed to work. And so you can see that in theory, yes, if the vapor can move through the entire structure without meeting the dew point, then this in principle will indeed work. So let's take a look at what can happen again with the non-vapor permeable layer. So here we go back to the diagram where we've got that situation, and I've put in an arrow which demonstrates that really the water is going to go down the pitch and is likely to saturate into timbers or anything that is going to absorb it. So that is the danger, that if the water vapor turns to water as a liquid, then obviously it's going to be absorbed into a lot of the structural timbers, causing problems. Now there are some systems out there that say that they have cracked this and they have got BBA certificates to this effect. So we're going to take a look to see how these systems operate in principle. So the way that these systems work is they introduce a gap between the foam and the non-vapor permeable underfelt. And the way that this is achieved is by including a cardboard fill between the rafters, and then the foam is sprayed to that. So the principle being that the water vapor goes through the vapor permeable foam, enters into a void area, and that I presume that ventilation or some lesser pressure allows the water vapor to escape. Now there are problems with this as far as I can see, and is that is a very narrow window of theory for it to work. If you imagine that at the top of the roof you've got the ridge board, and at the bottom of the roof you've got the eaves, and that you've placed these strips of cardboard between each and every single rafter. So in essence there is a bay of this detail along the roof. It's not continuous across the roof. There's no suggestion that there is any cross battening. So each individual space between each rafter has this detail, and therefore I can see that, you know, if there's no continuous ridge ventilation or no continuous eaves ventilation, then this diagram is going to be very, very difficult to achieve on site. But that's the theory, and that is how the BBA certificates for these particular systems are written. But they do have some very, very strict caveats in them as to how these need to be set up on site for this principle in theory to work in practice. And so finally, the obvious option that is a problem is we haven't thought about water coming in the other way. And every single BBA certificate that I've read mentions this, and that this has to be tackled before the foam can be applied. So here in my diagram, I've sort of reverted back to the original diagram I did. So I put the rafters back, put the ceiling back, generally put the principle of the warm air and the vapor rising into the roof space. But what I've done now is obviously put rain in, and assuming that the tiles may have some cracks in them, or that they're loose, or the flashing detail is not correct, wind-driven rain can get in. Obviously that saturates the timbers. They are embedded in the foam. This reduces the rate at which that can evaporate, and the theory goes that if timber reaches above 18% humidity, this can make it vulnerable to more particularly fungal, and if it gets even higher, wet rots. So this is the perceived danger of all of the types of foams, whether they be vapor permeable or not, that they slow down the natural evaporative effect of any water that might get in, and that really in principle they will only work in the long term if the roof remains watertight. And again, this is covered in most of the BBA certificates, and so it's very important that the roof is and remains watertight throughout the entire time that the foam is expected to perform. So where are we then with all this information? I think the underlying principle is that we know that from the science of water, and that the way it moves through materials, it is capable of moving through vapor permeable materials, and that is all fine as long as it does not meet the dew point, and that the way in which the materials have been put together are consistent with the caveats of the BBA certificates. So it's interesting to note that the BBA certificates use theoretical models. They don't really use practical models, and therefore things like the vapor resistivity of the material is assumed that it will actually be set out like that on site, so that the model can be realized. Now this is an enormous leap of faith really, because unless you can show that that foam has been applied with perfectly consistent finish, perfectly consistent thickness within a tolerance, then I would suggest that it's going to be quite hard to show that any one particular application on any one particular roof is going to meet that requirement. So the foam industry has to really make sure that it leaves really detailed evidence that the roof has been inspected, what works were done to the roof before the spray foam was added, the confirmation of the type of underfelt that is present on the roof, that was also intact at the time, whether any space has been placed in between the foam and that material, whether that space is vented in accordance with the BBA certificate. So there's a lot that needs to be left behind on site before a surveyor can even begin to decide whether this material is going to perform in the future. So we have in this product a situation which is quite common in modern construction now, is that things are modelled and work in theory, but can that be shown in practice, and can it be proven that it has been applied correctly to give surveyors and lenders sufficient reliable information that this material is going to perform as we would expect. And this is where the problem lies with spray foam at the moment in time. Now, I know the foam industry and its trade body are working on paperwork, but I do know that some installers and some manufacturers are saying that their foam is being applied to the new protocol. Well, the problem with that is the protocol is not an installation protocol. It is the protocol of how to assess foam during a visual inspection for pre-purchase reasons. So you can't actually apply foams to the principles of the protocol. All you can do is provide that very, very small window that the protocol suggests could be achievable to provide the surveyor with the evidence in paperwork form that they can realistically assess and draw some conclusion. So this is the problem that we're having at the moment, and until that is specifically resolved, I think this one is going to run and run.